Imagine a world where the invisible becomes visible, where the mysteries of the smallest particles in our universe are unveiled. This is the realm of MALS technology, a domain that has seen remarkable evolution over the past 2 decades. In the late 2000s, MALS was a promising yet limited tool. It was capable of studying the properties of macromolecules in solution, determining parameters such as molecular weight and size distribution of polymers, proteins, nanoparticles. However, it had its limitations, constrained by a single angle of analysis and an absence of integration with other analytical techniques. Fast forward to the present day, and MALS technology has undergone a transformation. It has expanded its wings and soared to new heights, integrating seamlessly with other analytical techniques like size-exclusion chromatography and high-performance liquid chromatography. These combinations have unlocked the door to more detailed information about samples, allowing us to determine molecular weight and size as a function of elution time. But that's not all. The introduction of multi-angle detectors has revolutionized the way we use MALS. By measuring the scattering intensity at multiple angles, we can now sidestep the limitations of traditional single-angle light scattering techniques. This means we can more accurately determine molecular weight, size, and shape parameters. And it doesn't stop there. The last 2 decades have also brought significant improvements in detector sensitivity and data analysis algorithms. Today's MALS instruments feature automated data acquisition and analysis capabilities. This reduces the time and effort required for measurements and data interpretation, making the process more efficient and reliable. These advancements have propelled MALS into new fields of application. From polymer science to biophysics, nanotechnology to pharmaceutical research, MALS has become an essential tool for investigating the structure and behavior of macromolecules in solution. So what does the future hold for MALS technology? The possibilities are endless. From even more precise measurements to integration with emerging analytical techniques, the evolution of MALS is far from over. As we continue to refine and expand this technology, we can expect to gain even deeper insights into the properties and interactions of macromolecules. In a nutshell, the past 20 years have been a journey of discovery and innovation for MALS technology. With advancements in instrument design, data analysis algorithms, and integration with other analytical techniques, MALS has transformed from a promising tool into a powerful ally in the quest to understand the smallest particles in our universe. And as we look to the future, there's no doubt that the best is yet to come.
And this the intensity of light, and this the correlated for the sign of the angle, and we will see it. This will only for the solvent. After this I have to prepare my sample, and my sample is, I will try to dilute the sample before, because because I never with plan for enzyme mobilization and grafting and just for training, and now I remember my private. I found very interesting subject for measuring this degradation occurred for polymers, carbohydrate polymers like starch or dextrine, but we are focusing only for starch because there is not enough time. Now it's 0.45 microliter filter and try to filtrate diluted solutions of cyanocated starch. Cyanocated starch means that put it in reactor for ultrasound reactor for certain time, and this will occur some kind of degradation of this polycarbohydrate polymer solution. I bought it. And now also pour the sample with a stone. Could you show the solvent? Yeah. This is the solvent sample. Yes.
we
And
see.
then
Wow.
and then the Carine solution, this chamber inside. Thank you for this. And then the solvent solution that will be measured. And also, and then the measure will continue. To see one sample of my measurements. Let us see. Yeah, sonicated sample. This is the 0 time for sonicated sample. Yeah, this is 0 time, and this is calculation and exponential. We say exponential, and this concentration, several kind of concentration for several angle, and this exponential to 0 for several concentration, and this for several angle to get molecular weight for concentration. When going to 0, exponential to 0, it was 12 millions, and also for the angle, and the relative difference of molecular weight is slightly, it's very low because it is 3.15, 10 exponential to minus 4. And what's the most important here is the radius of gyration. The radius of gyration effect of ultrasound. We got this for 12 minutes. We can recognize that the radius of gyration is 106. Are going more for, I don't like to print. If are going more to database to choice 224 minutes, and calculate, we will found the radius of gyration is 100.